then try to find the correlation functions, and okay, and then say that how this the partition functions can be written in something I call the matrix product state. Okay, so that's what I do. So what we are going to learn is Ising model. So Ising model in 1D. 1D means 1D is the special dimension, one dimension. And here we will have this transfer matrix. Okay. On is the red light? Is it on?
Oh, now it's on. Now it's on.
And now it's on. Okay. So I'll then talk about transfer matrix. Okay, my handwriting is small, so if it is not visible, please let me know, and please stop me if I'm fast. Okay. So I will say that transfer matrix methods. Okay. So what I'm going to do is that usually there is a transfer matrix in Ising model, but why I'm calling it as a method is that I want to extend it to other models also. So this is general method. Okay. And then I try to find out correlation functions. Okay. So, okay. So I think this is the basic thing which we want to do today. So to start with, the Ising model, I also introduced it in the previous class, that the Ising model is in one dimension is the simplest model, because if you want to model a system, you need a space. Here I take a space which is one dimensional lattice, which means that you have these are the lattice sides. The lines are not there, the points, like these are the lattice sides. This is my space. So whatever my variable will live only on the lattice sides. Okay. So the lines is just for guiding the eye. It's just the points. Okay. So at each point, so let us call the point name is its I. The site name is I, and at each point we have a variable called Si. Okay. So Si is my variable, or the one I want to represent. These are my basic units which will do certain things. Okay. So this is my variable Si. And this is I, means this is I plus 1, this is I minus 1, and this is Si plus 1, this is Si minus 1, and each of Si will take a value. Okay. So that I say that it's just a two variable problem, so you can call it plus minus 0 1 iron copper if it is a alloy. So it depends on your description, how you describe. So it's a two symbolic things. I can call it plus minus, which in this in Ising model I describe it as a plus minus, but it can be also 1 0. I mean plus and minus is 1 and 0, or it can be A B. I do not know what A B are, or it can be any other thing, like whatever you want, iron and copper. Let us say iron or copper, or it presence and absence also. This is presence and absence. Presence of a particle and absence of a particle. So you can denote it whichever way you like. Okay. So this is this is the second step of the modeling, right? You need to know the dimension. You need to know what variables you have at the lattice, and then, of course, you have to think of the boundary condition. When you talk of the lattice, what is the boundaries, right? You have to bother about that. We can take open boundary, closed boundary, whatever. We decide it later. Okay. So each point you can, at each point on the lattice, you have a variable Si which can take values 0 or 1. In a second description, it can take a value A or B.
You mean each particle at site I?
No, particle is no. So you can, you can call it spin. If you call it plus and minus, I call it or up and down, or you can call it also up and down. So you can call it, right. Two-level system is a what? Each site has two values. It takes two values, like or you can call it people who are standing with colored shirts, like so each site you can have a person standing here. Each of the person has a yellow shirt or a red shirt. So everybody can be in the red set, everybody can be in the yellow set, somebody yellow, somebody red, whatever. So those are the, so how many configurations you have? So this is L, this is I equal to 1 to L. So this I call it I equal to 1 and this is I equal to L. So there are total number of configuration in the system. So I'm just saying that don't bother about the name, call it yellow, red, call it up, down, call it whatever, it doesn't matter. Okay, so that's what I'm saying. I will primarily follow a notation plus and minus, which is spin up and spin down. Okay. So the total number of configurations. So what is a configuration? So first I will let us say that the configuration, a configuration of a system is given by, if you specify at each site whatever you have, like yellow, 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 yellow is one configuration. Okay. So that I know my notation is that SI. Okay. I mean this means, this curly bracket means that all values are specified. Okay. So if you specify the all values like 1, 1, 1, 1, 1 or 1, 0, 1, 0, whatever you want to specify, each one is a configurations, and number of configuration, total number of configurations, total number of configurations, this equal to 2 to the power L. That's what you find out. Okay. So these are subsidiary, these are informations which are deriving, but as far as the modeling goes, you have only done 2 steps, like what is the lattice, and on the lattice what are the variables. So now you have to talk of interactions, right? I mean how these variables interact. So if I take SI equal to plus minus 1, I take this SI equal to plus minus 1, then right, I mean the one interaction in the interaction is that a neighbor, a site interact, this interacting with the neighbor. Okay. So you can take an interaction. So the interaction actually defines what your model is. Okay. I'm now writing something, some interaction. So minus summation over I SI plus 1. Okay, that's my interaction. So what you do is that you take the product of 2 consecutive sites. Okay, so basically if you take a configuration, for example one configuration, let us say this is plus minus minus plus minus minus something something. So now what you do is that for plus 1 plus minus, this is minus 1, this is plus 1, this is minus 1, this is minus 1, like that. So and then you are summing them. So minus 1 plus 1, whatever it comes up. Okay, so that becomes the energy. Okay, the Hamilton. No, you can take plus. I don't have a problem. Let us say the first one is that summation over SI. You can define, the model is defined by whatever you write, right? You can say that 3 of them, product of 3 or whatever, right? I mean, so that defines your model. I am taking a specific one. Okay. So if you take, for example, if you just summation of SI, that's a very simple one. If you have not done it, then let us do that little complicated one, and then you reduce to the simple one, as one shot. Just like that. Okay. So you might think of product of 3. Okay. But product of 3 will give you same plus minus 1, right? Little complicated, but it is also the same plus minus 1. You don't go very far with just plus 1 and minus 1, right? I mean, so this is the simplest one I'm talking about, SI and SI plus 1. Okay. So let us stick to this for the time being. Minus also you have to there is a minus here. So if you want an interaction strength, you can put a J here also. There is an interaction strength.
SI plus or minus? The minus one is not there or what he is asking. Okay, automatically will take care of that. No, what he is run I. Okay.
His question was, if you only take the right side one, left side is not accounted. He thought.
But the next I will become.
Yeah. Product of 2, na. So basically, let us write it, explicitly write it. So this is minus J. So this is S1, S2 plus S2, S3 plus S3, S4, and then similarly SL minus 1, SL. If it is open boundary, let us write it. Okay, SL minus 1, SL. And if it is closed boundary, you have one more. So if you have a periodic boundary, you have one more term. This L and then 1. So SL S1. You have. So this is open boundary. This is, let us call it open boundary. Open boundary. And in a closed boundary, you have another term. So whatever here plus SL S1. So this is closed boundary. Okay. We'll come to that. So why not negative, why positive? So it is right, right? I mean, I'm putting a negative, I'm assuming the j is positive. Otherwise, there is no j is positive. So what does it simplify? Okay, so we'll do that. We'll come there. That question will answer. Any other question here? So you know the configurations. There are 2 to the power L configurations. And can somebody tell me if what is the energy? It is the energy functions. You can call it H, or this will give you total energy of the configurations. Okay. So I'm just saying that E energy. So let me ask you a question. So E of a configuration which is summation over Si, all Si equal to +1. Okay. So what is the energy in open boundary situation? Huh? If all of them are, so basically all of them are +1, so all of them are plus. So how this here is plus, and how many bonds are there? L minus 1j. Okay, so this equal to minus of L minus 1j. So this is in open boundary. Okay, so in period, so this is in open boundary. And what is the same in the periodic boundaries? L. So this is Lj minus Lj. Okay. So that's the energy of one configuration. But you know energy, if I give you any other configurations, you will be able to calculate it, right? You just make a product, whatever. So every configuration has some energy, right? I mean, so every configuration has some energy, and that is I call E of C in general. That is energy of a configuration is E of C. So this is energy of a configuration. Okay. So now if I ask you, so I ask a reverse question. How many configurations are there with energy minus Lj? Which are they? So all of them plus or all of them minus, okay? So open boundary situations, let us for the time being drop, and we'll take this term and we'll only deal with closed boundary. I mean, whenever open boundary, you can again introduce it when it is needed, okay? So this is the energy of the configurations, and so there are 2 configurations of energy minus Lj, okay? Because all of them can be plus, all of them can be. Can you tell me what is the next energy you can have? Higher energy, this is the lowest. What is the next one? One is flip. So what is its energy? L minus 2. Yes, okay. So basically what will the energies of the system will, because if you flip one, this one is contributing, both of them are plus. If you flip, both of them will be negative. So how much? L minus 2 or L minus 4? Because it was, these two sides was counting as +1. Now they will count as -1. So it is L minus 4. Okay. So the next energy is Lj, and the next energy is actually Lj, and the second energy. And how many configurations are there with that energy? L configurations, because you can flip any of them, right? I mean, if it's a periodic one, are you getting? Is it okay? Are you getting with? Are you with me? Yeah. Okay.
Actually, there's 2 times here.
2 times.
You can start with all up and flip one down, and you can start with all down.
Yeah, I can flip all up. Yeah. Okay. Yeah. So there are 2, right? I mean, L and yeah. Okay. Yeah. Each of them you can flip. So each configuration you can actually just flip it, and then you still have the same thing. Okay. The whole configuration, if you flip, you have the same energy. So that's a symmetry. Okay. So this model, if you take Si goes to minus Si, this energy is conserved, right? I mean, this is also minus, this is minus. So Si goes to minus and Si, the energy of the system is the same, remains same. If you just flip all the spins, then the energy of the system remains same. That's a symmetry, and so it's a flipping symmetry. Can anybody identify what symmetry is this? Okay. Okay, let's don't name it. It's called Z2. It's a 2-state, so discrete symmetry with 2. Okay, so we'll not go there. It is not needed here. So this is basically the configuration. So this is the total energy of the system, and for each energy, you know how many configurations are there. Okay, so that you call, for a given energy, the number of configuration for a given energy, you can call it omega E. That's a degeneracy of a given energy, right? I mean, and you can calculate actually how many configurations are there for a given energy, like one you calculated, right? I mean, the others are complicated, a little difficult to calculate, but we will not do that. Omega is the number of configurations with a given number of configurations with energy E, with energy equal to E. Okay, so that's the omega E. So this is my Hamiltonian, and then so what does the point is that why I am doing this Hamiltonian, and what is the meaning of this negative sign. So you can see that the minimum energy in this situation, you get the minimum energy only when all of them are the same sign. Plus or minus you do not know, because all of plus is the same energy as all of minus, but all of them has to be the same sign. Okay, so so that kind of state, when all spins are aligned in one direction, or all of them are plus, you call it a magnetic state, right? I mean, it's the so that's the magnetic state, and that's the one. And what kind of magnet it is? If all spins are aligned up, ferromagnet. So this is a ferromagnetic system. So by putting a minus sign here, what I am assuring is that the minimum energy configuration is when all spins are up. So this is a ferromagnetic. So this is a ferromagnetic Ising model. Okay. So now, by the way, as I said that instead of taking this as a Hamiltonian, you can take any other variable, like any other variable. It doesn't matter. So the same Hamiltonian can also be written equivalently, that minus j summation over delta, which is a Kronecker delta function, the delta Si and Si plus 1. Okay. So then this delta ensures that whenever these two things are same, you have minus j. If they are different, the energy is 0. Here, when they are different, the energy is plus j. Okay. So this is just a shifting in energy one, and it's the same equivalent Hamiltonian. So if you have, so in this description, Si can be 1, 0, AB, iron, copper, or whatever you want to write. It's the same Hamiltonian, and it's the same description. So it's just some shifting of energy, that doesn't matter. Okay. So we'll follow this notation, but this can be written in other notations also. Okay. So next thing is that, so now we know the configuration. So what was our description of a statistical system? Is that the system actually evolves from one configuration to the other. So right, I mean, so if you start with, right, I mean, some configuration. Let us say that you start with a configuration plus, plus, minus, plus, or something, some configuration like that. And your dynamics is that maybe you want to, the spins are flipped, right? I mean, if you flip a spin, the configuration of the system will change, right? So let us flip this one. So if you flip this one, this becomes minus. So this was plus, and you have a new configuration, which is plus, plus, minus, 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 like that. So this is the new configuration. So basically, in the configuration space, which is 2 to the power L configurations, like 2 to the power L configurations, the system, right, I mean, with time, the system is actually evolving by changing from one configuration to the other. The example which I gave with 7 SOPs is now 2 to the power L SOPs, and you have a rule. We'll come back to the rule little later, and what rule, how the system is moving, that will come back later. But what is what we know from statistical physics is that energy, if the energy of a configuration is whatever E, then probability, if the system is in temperature T, then probability of getting a configuration, so this is equal to E to the power, in the stationary state, this is proportional to E to the power minus beta E of C, right? I mean, this is what is already given. Okay. So now I'm reminding you this example, right? I mean, I emphasize a lot in my previous example that if you have 8 configurations and you keep moving in that configuration with whatever rule, you reach a stationary state, right? I mean, you reach a stationary state, which means the fraction of time you visit one particular configuration do not change in time any further, right? I mean, it doesn't change anymore. Okay, so that has a limit. The number of times, the fraction of times you visit one particular configuration has a limit. Okay, so given a rule, right? I mean, you should know how to calculate that number, right? How often you visit SOP number 7, okay? So that is something you have to calculate, okay? So that is a tough task sometimes. So here in equilibrium, okay, in a system which is in equilibrium, this calculation is, you don't have to do, it is already been said by somebody, okay? So there is a general description of what is the probability of finding the configuration, a given configuration, okay, in stationary state, that is given, okay? So that is given by probability of C is e to the, so, okay, e to the power minus beta EC.
Equilibrium or stationary?
In equilibrium. This is in equilibrium, only in equilibrium, okay? So this is given that it is that's the only statement in equilibrium, okay? This is another statement in equilibrium, okay? So equilibrium satisfies total balance, and equilibrium has also Boltzmann distribution. So now question that how often SOP number 7 will be visited is e to the power minus beta, which carries the information about the temperature, temperature bar, and energy of that configuration. So it's proportional to exponent, e to the power minus beta e. That's the one. So now if you say, which one? No, stationary state doesn't have a time dependence. So you are not talking about how.
I am saying that suppose I have write down the rule and the rule has some time dependence explicitly. Then can I achieve the stationary state or not?
Yes, you can have a stationary, but you have to ask question, what is stationary there? One can have a stationary state. For example, you can have a system where the temperature is oscillating, or maybe both ends the temperature is oscillating, right? I mean, it's constantly oscillating. So question that will become stationary, right? I mean, yes, it is stationary, but you have to redefine what you mean by stationary, okay? So, right, I mean, I don't want to, maybe you can discuss it later, or maybe the short answer is that, so if you have oscillations, you will create a, you have a phase, okay? So what you have is that if you fix the phase, like, you are oscillating like that, like, you are oscillating like that. So, if you are here, you are at a particular phase, okay? If you are here, you are at a different phase. So after some time, right, in a very long time, if you oscillate like that, so now what you do is that you take a configuration of the system at a given phase, like here. Next time it goes, when it is here, you take a snapshot. When it is here, you take a snapshot. So for a given phase, the configurations will not evolve anymore, okay? So that becomes stationary. But if you change the phase, it's a different stationary state. So you can calculate, some simple situations you can calculate what is the stationary state, but one can.
So in that case, the energy should not depend.
But then when you have this kind of driving, anyway you are out of equilibrium, right? I mean, usually.
Energy is not a conserved quantity.
Which is not a conserved quantity anymore. Energy is not a conserved quantity, right? I mean, generally energy may not be defined in equilibrium kind of non-equilibrium kind of systems. Okay. So basically here I am assuming that the rule doesn't have any time dependence, but the probability of, right? I mean, you may start with one particular configuration, everything is up, but with time actually you generate different configurations with a different probability. The probability, okay, for a given configuration, in stationary state is given by that. Okay. So now, actually, when I write a probability like that, I'm just always putting a mark like that, because this is not normalized, right? I mean, you have to normalize it. For every configuration, there is a probability, but sum of probability of all configurations must be 1. So that basically, let us write that. So probability of C is that. So if I want to write that, you have a normalization factor here, and then so P equal to, if I want to write, there is a proportionality constant here, okay, N. So then I have to write that probability of C, this summation of, so that means if I want normalization, summation over C, N is here, e to the power minus beta E of C, that has to be 1, okay. So then N equal to 1 divided by this one, okay. So I can write, so the actual equation, so basically the full thing is that probability of C, so we also get probability of a configuration. So this is e to the power minus beta E of C divided by 1 divided by this one, N. N is 1 divided by N times that, so divide by that. So divide by summation over C e to the power minus beta E of C. Okay. So summation over C e to the power minus beta E of C, and this one you can define some other thing, because this will come as a normalization constant, repeatedly it will come, and you call it Z, the partition function. Okay. So partition function is just the inverse normalization constant of the probability here. Okay, it's not very. So that we define as Z, and that's Z. Okay. So what you need to know is that if you know the partition function, okay, to know the probability, you just need to know e to the power minus beta energy of the. You need to know the energy of the configuration and the partition function. Okay. So if the configuration is given the energy Hamiltonian like that, you can anyway calculate the energy, right? I mean, it's okay. And then all you need to know what is this number, right? I mean, this number. Okay? So that's called partition function, and you want to calculate it for this model now. Questions? Okay. Okay. I think I can go to the other part of the board. So the partition function, as I see that partition function, this equal to summation over C, all configurations, e to the power minus beta e of C. Okay. Okay. So okay, let us do one more thing here. Okay, so the partition function is this. So let me calculate this first then. Okay, so this is summation over C, and what do you mean by summation over all configurations? How do you get all configurations? It's like each S1 and S2 and S3 and S4, each of them can be plus and minus. So you take all S1 equal to plus minus, S2 equal to plus minus like that. So this can be written as this sum is same thing as sum S1 equal to plus or minus, summation over S2 equal to plus or minus, summation over SL dot 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 SL equal to plus or minus, right? So this configuration is 2 to the power L. This sum is 2 to the power L. And this sum is also 2 to the power L, right? I mean, if you take plus, 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 you will one term, plus, plus, minus, whatever, minus, minus, minus is another term, plus, plus. So this is all configuration, right? I mean, you agree with this. So the all configurations means this, okay? And then e to the power minus beta EC, we are writing that, e to the power minus beta. And then you have E is given by this one, okay? You can take it from here or you can take it from here, right? So this is e to the power minus beta, and there is a minus sign there. So this is e to the power plus beta j times S1 S2 plus S2 S3 like that, SL minus 1 SL, and if it is a periodic boundary condition, you have also SL S1. Okay. So that's what you have to calculate. That's your partition function. Okay. Okay. So now what we do is that, so this one can also be written as like, instead of writing that, you can break this as a product because this is just a sum. So this one I'm again writing it. So this is summation over S1, S2, S3, SL, and this one is e to the power plus beta j. So you can see that whenever beta comes, j comes along with it. Okay, you can dump it with beta. Okay, so there is no way the system would know what is beta and what is j independently. The temperature and the interaction, the inverse temperature, this will come as a it's just come as a multiplicative factor. There is no way to distinguish them in the system. So basically, you can always either you can drop that, it's not needed, or you can redefine that to be a k. Okay, so you can. I'm just dropping that. There is no need, and I just put it. I don't want to carry this number beta. This j, j can be set generally to 1. Okay, and that's a pretty general statement. Like if you have a Hamiltonian is defined something like that, you can always rescale by one parameter. Okay, whatever parameter that becomes your unit of energy. Okay, so you can rescale that, and I'm just rescaling. My energy unit is such that j is 1. Yeah, I'm measuring energy in units of j. So that's the meaning of that. So e to the power beta and this. So now this is e to the power beta.
I guess another way to say it is whatever rescaling you do, the beta times j would remain the same.
Yeah. Yes. So yeah. Beta times j always remain the same. Yeah. Okay. Okay. So now this is e to the power beta S1 S2. E to the power beta S2 S3, e to the power beta S3 S4, like that. e to the power beta SL S1. Okay, so this is the sum, but all these sums are there. Okay, S1 and S2. So now can you do this sum? I mean, if you can do the sum, you can get you can get the partition function. So can you do this sum? So let us try doing one of the sum. Let us say take you have all these sums S1 equal to plus minus, or maybe let us take the sum of S2. But then S2 appears here and here, right? So you have to take this. So basically, if you want to do S2 sum, it will be e to the power minus beta S1 plus. Here also you have to plus. Then it's complex, pretty complex. So it's coupled to each other. So there is no way, right? I mean, one by one you can do the sum. That kind of trick will not work. So that's the one we use a different trick. So what I say is that this one it defines a function, some function. This function depends on S1 and S2, right? So if I call this is a function of f or f S1 S2, this will be same f S2 S3. Okay, so I call it g S1 S. Okay, I call it the function g S1 S2, and this is g S2 S3, like that. This is the same function, and that last one is g SL S1. Okay. So so now it doesn't help, right? I mean, you still have this. So one can think that another way to think is that this is a function of S1 and S2, but you can think that this is how many values are there. This is a function I'm saying, but S1 and S2 are not continuous variables, right? I mean, how many values you have? 4 values, because S1 can be plus, this can be plus, 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 minus. So there are 4 values. Okay. So let us arrange them in a matrix. Okay. So this is like plus, 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 minus, plus, minus. So all the values, like here I have g of plus plus, because this is plus plus, g plus minus, and g minus plus, g minus minus. And do you know what is g plus plus? E to the power beta. Okay. So g plus, so similarly g plus minus is e to the power minus beta, and this is basically e to the power beta, e to the power minus beta, e to the power minus beta, and e to the power beta. Okay, so this is the matrix. So one can think that if you have a specific, so for one particular configuration, for example, S1 and S2 will have some specific value. Okay, so that is the matrix element, S1 S2 metric element of this matrix, right? So if you think this matrix as T, okay, if I call this matrix as T, so G S1 S2 can be thought as a T matrix element S1 S2. Right? If you take plus plus, then you have T plus plus, this element, right? I mean, this is T plus plus. If you have plus minus, then this is T plus minus, right? I mean, this one you get. Okay? Are you? No, the teachers, right? Okay, fine. So so T S1 S2, and this is the one. So this is T S1 S2. So I will use a notation what Arnav was using, and that is pretty nice. So I will use that. So T S1 S2. So for a matrix, so you can write this element. Usually you say that 1 2, right? 1 1 1 2, 2 1 2 2, right? I mean, but the symbols doesn't matter. As I say that you can call it 1 0 1 2, call it whatever, A B plus minus, doesn't matter. It's a matrix. So the other way to write a matrix is that if you want to this element, you know this, no? I mean, this one can be written as T plus plus, right? I mean, this is another way of writing T plus plus. So T plus plus equal to T this, or T S1 S2 equal to S1 T S2. This is also the matrix element of T, S1 S2 element of matrix T, right? I mean, this is another way of writing this. So I will use this notation. In case you are not, I think people are familiar, but in case you are not familiar, this plus is a matrix. So sorry, plus is a vector. So plus is actually, you can call it 1 0, and minus equal to 0 1. Okay. So multiply this matrix like that. So this one basically means that 1 0 e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta times 1 0. If you multiply, you just get e to the power beta. Okay. So that's the meaning of this is by plus, and this is T, and this is again this is plus. Okay, this vector is plus. So this is just t plus t plus t plus. Okay, so you multiply, you get this. Okay, so that's the way that's the notation. So t s1 s2, instead of writing t s1 s2, I write so I write this one as s1 t s2. Okay. So the next element g s2 s3, but that is t s2 s3. So that is basically s2 t s3, and then s3 t s4, like that. And if you go like that, the last one will be sl t s1. Okay. So now the sum, I will just erase all that. T plus plus t I want to keep, of course. So t equal to that matrix is there, and the notation is now clear. And let me. So this one, the last term is sl t s1. Okay. So now I erase all these definitions. This is also not needed. So now I still have this sum, like this summation over s1 equal to plus minus, summation over s2 equal to plus minus. Okay, and then all this term. So this is equal to that, Okay, and t is the matrix, and now I know. It's fine with. So now what I do is that let me take now I try to take the sums, like then summation over sl equal to plus and minus. So this is s2. Okay. So now let me take one sum. Let us say take the sum of s2. Okay. So I take it, erase it here, and s2 appears only here and here. Okay. So I just write wherever the sum appears. So this is summation over s2 equal to plus minus. There is nowhere else there is s2. Okay. So now this s2 equal to plus minus, this one, do you know what it is? Is this clear to you? That this is the identity matrix, this is a completeness relation. Okay. So this is basically in the same notation. If you say that plus plus, plus minus minus, this equal to identity matrix. Okay. So if you write, this plus, this is a matrix again. So this matrix is 1 0 times, no, the other one, 1 0 plus this is 0 1 times 0 1. So this is a matrix. So that is basically 1 0 0 0. This matrix is this, plus this matrix is 0 1 0 0 0 1. You multiply that. 0 times 0 is 0, 0 times 1 is 0 times 1 is 0, 1 times 0 0, 1 times 1 is 1. So that's the identity matrix. Okay. So that's the general property of the vector space. So you have this completeness relation. Okay. So plus 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 minus minus is this matrix plus that matrix is identity. Okay. So this one can be erased totally, and it can be said identity. So similarly, there was a sum of s3 here. Now I take s3, and s3 appears only here. Okay. So I can also erase it from s3 here and put s3 here. Okay. So except this s1, which is appearing both sides, all of them I can erase, right? Because this is an identity matrix. Okay. So ti is just t. So I can erase this completely. So I erase that. T remains, but all other things are erased. This is t, and summation over s3, that is also erased. S4 will also erased. All SL is erased, but the T's will remain. Okay. So how many T's are there? Right? For S2, so all of them you have taken S1, S2, S3. If it is a periodic boundary conditions, all L minus 1 you have taken. So T to the power, write T to the power L. Okay. So all the T's you have taken. So this is just T to the power L, S1, S1. Okay. Okay. So all these sums are gone also. All these sums are gone. Only S1 sum is there. So this equal to summation over S1, S1 T to the power L, S1. So now if you look at that, if S1 equal to also plus minus, so T to the power L is a matrix, right? T to the power L is some matrix like here, 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 here. And if you put S1 equal to plus, that means this element, and S1 equal to minus, that is this element. So basically it's just sum of this and that. Okay. Okay. So that what it is called? trace of the matrix T to the power L. So this can be written as trace of T to the power L. Okay, T to the power L. So this is what we get. So now let me quickly ask you to do this exercise and maybe with me. So question is that instead, let us say that you have a open boundary condition, and S1 is something I specify. Okay, let us say S1 is plus given, or something I will specify later. S1 I don't know, and you have an open thing like S1 to up to SL. So can you tell me what will be this partition function now? Why? Get SL, yes. No, okay, so let us do that. The problem is clear. So basically, let us say that you have an Ising chain like that, and first pin, I mean, it's the example that first one is plus and last one is minus. That's given. You cannot change that. So basically, so if you want to do that, let us do this. So for the periodic boundary condition, we find that this is trace of T to the power L for periodic boundary conditions or on a ring. Okay, so this is what we find. So now try to find it in an open boundary condition. Okay. So now in that case, S1 sum you don't have S1 sum. Let us just redo this. S1 sum you don't have. SL also is fixed, so you cannot take whatever you want. S1 and S2 I will fix it later because the boundaries I will whatever I give you. And then in the only S2 sum is there. So this S2 and everything will go. The last one, this SL and S1, this term is not there. Okay. So instead the last term is just SL minus 1, right? I mean SL minus 1 and SL minus 1 T SL. Okay. So this term was there. T was here also there was a T here. Okay. So basically this SL minus 1 sum, this is also go. So how many T's are there now? T to the power L minus 1. So that is basically T to the power L minus 1 you get from here, these T's, and the last term which is now SL that will remain there. Okay. So the partition function, this is periodic boundary conditions, and the partition function, so this now I think, no, let it be here. So this I'll erase it here. So now my partition function, what I get, Z equal to trace of T to the power L if it is periodic boundary condition, and this equal to S1 T SL, it is open boundary conditions. So now let us say that instead of fixing S1 to be, so basically if it is S1 is plus and SL is minus, then you still have this T to the power L elements, but L minus 1.
No. I mean,
T to the power L minus 1 there. So now, so let us write it correctly. T to the power L minus 1 SL. Okay. So these are the boundaries now. Okay. So these boundaries are there. So now, so for a very simple example, like if S1 is plus, SL is minus, from the matrix, which are the one you want to pick up? This one. Okay. So this is the only, this element is your partition function. So you find T to the power L and find only that element. That's your partition function. Okay. So we keep it there, and T is also given here. Okay. So now, can you calculate it? What is trace of T to the power L? Achha, can you calculate, for example, we will not go to trace, we will do it in a, because we have the other thing to calculate. Can you find any matrix to the power 3 or 7 or whatever, 25, L can be anything, some matrix to the power 20. How do you do this? Yeah, please. So what is how do diagonalize? How to find them? Like yeah, okay, probably, yeah, you know. So anyone knows how to diagonalize a matrix? Okay, yes, there is a similarity transformation, but how to find the matrix? Procedure, Eigen Vectors. Okay, so for just quickly, let me just tell you that if you have a matrix, so basically you have some matrix. So your eigenvalue equations, this that M, some matrix M, and this is EI. So this is lambda I EI, right? I mean whatever the dimension. Okay, so this is your matrix. Okay, so the same equation. So how many equations are there? whatever the dimension of the matrix, right? I mean, that many equations are there. So this same equation, because there are L such equations, like, D such equations, you can write it M times this, all of them, like, you can write it as a, like, E1, E2, E3, like that. If you write like that, this becomes a matrix because each of them is a column, okay? So now this one will be, you can just check this, lambda 1, lambda 2, lambda d, and times the same matrix here, right? I mean, this is the same, from equal to E1, E2, EL, ED, whatever the dimension of this one, times that, okay? So I'm saying that the same equation can be written as, if you write this column, these columns, there are d such columns, you put them together, it becomes a matrix. So all the set of equations can be written as M times that equal to lambda. If you put all them in the diagonal one, everything else is 0. So this is a diagonal matrix, and you have to put the same matrix here, okay? So the equation, what you call eigenvalue equation, can always be written as mu equal to ud. Mu, if you call this matrix as U, that equal to mu equal to ud. Well, that's the same thing as the eigenvalue. If you have eigenvalues, you can write eigenvalue equation is the same equation as mu equal to ud. So now, if that is the case, then what you have is that m equal to u d u inverse. So maybe you have very frustrated situations, you may not have a inverse, but those we skip, not for today. But otherwise, m can be written as u d u inverse. That's what you call a similarity transformation. Then if you say that m to the power n, m to the power some n k, m to the power some k is an integer, need not be integer. I mean, you don't need to, it doesn't have to be integer. But if this is to the power k, then this is u d u inverse, right? I mean, let's say this is equal to 2, then this is, so this is equal to m to the power k, m equal to that. So m to the power k equal to u d to the power k u inverse. You agree with that? Because if it is 2, then multiply this u inverse cancels, kind of thing. So this is gone, right? So this is the way to find the eigenvectors. So for this matrix, this is a simple matrix, and let us find the eigenvalues and eigenvectors.
You use the letter u, but u need not be unitary.
U need not be unitary. Okay. So this is, I know. So yeah, it's some matrix A. Okay. So this is not a unitary matrix, but this equation is always true, right? I mean, mu equal to ud. So I mean, all I'm saying is that instead of remembering the eigenvalues equation, the equations are this. The set of equations are mu equal to ud. That's the equation. Okay. So then m to the power k is u d to the power k u inverse, and you can write that. So basically, if here the matrix T, where is my matrix T? Yeah, here. So here the matrix T is this. It's a 2 by 2 matrix. So here getting the eigenvalues is easy. Okay. How do you get? So there is a trace. So basically lambda plus minus. So trace of the matrix is sum of the eigenvalues, and the determinant is just the product. So this is lambda plus minus equal to trace minus square root of trace square plus 4 determinant divided by 2, because this is sum of them, and this is trace square is a plus, right, minus 4 determinant. So this is the product. So this one is lambda plus minus lambda minus. So lambda plus and lambda minus are lambda plus lambda minus plus minus that. Okay. So lambda plus minus is just plus minus that. So this is basically lambda plus lambda minus. This is lambda plus lambda minus. So this is just that. Okay. So that's the formula. So can you now find me out what are lambda plus lambda minus in this situation? So anybody? Okay, so yeah. So this is e to the power beta. So let me write it, e to the power beta. So lambda plus minus equal to e to the power beta plus minus e to the power minus beta. Okay. Right, I mean, the sum anyway, the sum is 2 e to the power beta, which is true, and the product is just e to the power 2 beta minus e to the power minus 2 beta, which is also true. Okay. So this has to be this is the solution. Okay. So these are my lambda plus lambda minus. So now if it m to the power k is u d to the power k, trace of that equal to trace of that. Trace of u d to the power k u inverse, but then trace is cyclic, right? I mean, we can take this matrix here. Okay. So this is just trace of d to the power k, and d is contains only the eigenvalues in the diagonal, right? I mean, d is so. D, this D matrix, D equal to just lambda plus lambda minus 0 0. Okay. So d to the power k is just lambda plus to the power k, lambda minus to the power k, and trace of that is just lambda plus to the power k plus lambda minus to the power k. Is fine. So basically, what we have, this case you have lambda plus to the power k plus lambda minus to the power k. Sorry, L. Lambda minus to the power L. So this is kind of pretty clear. Okay. So now, can you tell me this? For that, there is no simple things like you cannot use this lambda plus, only eigenvalues will not work because you need u now. Okay. Because this one is t to the power L minus 1 has to be explicitly calculated, and you have to find out the corner element. Okay. For that you have to calculate it properly. So let me just quickly do that, and you can do it at leisure at home. Okay. So that's basically t equal to that. So now now let us call it what is the Eigen vectors. Okay. What is e plus and e plus and e minus? In this case, e plus is very simple, 1 0. Okay. So you can see that if you multiply that, it's not normalized, it's normalized also. E plus is this, and e minus equal to 0 1. Okay. This is fine. So if it is e plus and e minus, your u, this one u is just the collection of eigenvectors, right? I mean, you just make a collection of eigenvectors. So u equal to just 1 0. Sorry, I think this I'm wrong. 1 1 1 minus 1. Okay. So this is e plus is 1 1, e minus is 1 minus 1. So you can multiply that.
You have to normalize it before you write the matrix.
No, it is still inverse. It will take care. You don't need.
Okay, that's actually.
Yeah, because u is not my unitary. So yeah. So basically, this is my e plus is 1 1. So if you are doubtful, you can just multiply 1 1 here. What do you get if you multiply 1 1 here? If you multiply 1 1, these two will sum. First one, this plus that, this plus that. So this is just 1 1 times this eigenvector, right? So 1 1 is the eigenvector for lambda plus. Are you with me, sir? Okay. So so it's fine.
Yes.
Man, I don't want to lose people here. Then I mean, so it's okay, right? I mean, these are just I'm finding eigenvalues and eigenvectors. Okay. So so these are the eigenvectors. So now what is u? T equal to that. So now u, I take out that, and this is also gone. This is also gone. So now what I have is that now once I know the eigenvectors, I write u equal to just 1 1 1 minus 1. Okay, that's my u. Okay. So now t to the power k for any general k. So that is just 1 1 1 minus 1. That is u, and then you have to say that what is here, right? I mean, no. So this is lambda plus to the power k, lambda minus to the power k 0 0. This is d to the power k, and then u inverse. U inverse is 1. It is actually u inverse is here. It is same as u 1 minus 1. Just check it. Just I mean, and then there is a factor of half here. I mean, no. If you don't normalize, there is a factor of half here. Okay. So if you multiply all that, you do it yourself. So t to the power k, I just write what is the value of t to the power k, so that will be useful. So lambda plus minus that, and u equal to this, and t to the power k t to the power k equal to half of lambda plus to the power k plus lambda minus to the power k, lambda plus to the power k minus lambda minus to the power k, lambda plus to the power k minus lambda minus to the power k, and lambda plus to the power k plus lambda minus to the power k. Lambda plus to the power k plus lambda minus to the power k. Okay, so this is t to the power k, and so these are the things we know. Okay, so this is simply simple matrix multiplication. So what will be if S1 is plus, if first one is plus and last one is minus? So in that case, you have lambda plus to the power k minus lambda minus to the power k. Okay, instead of lambda plus to the power k plus lambda minus to the power k, you get a minus sign here. Okay, so that's for open boundary. Is it still okay? Okay, so we now know the partition function of the system. So you can take another example. For example, instead of S1 equal to plus or minus, you can take a free boundary, like it can be randomly oriented, like you do not know whether it is plus or minus. So half of plus or half it is minus, okay, with the probability. Okay, so then you can have a vector half, S1 can be a vector, it can be half of plus and half of minus, or you can take alpha of plus and 1 minus alpha of minus. You can take any boundary you like. Similarly, the other side you can take another boundary. You can calculate it, right? All you need to know is that this one, right? Whatever you have here, and some matrix elements will add up. Like if you have just plus minus, if you take all S1 and S2, then if it is, then all the elements will be there. Then you need sum of all the elements. Okay, so in some fraction, that will be your partition function. So you can calculate for open and closed boundaries, and now we'll try to calculate some other quantities. Because calculating the partition function is only on the way, like we only know the probability of the system completely, because our task is that P of C, all we want is P of C is e to the power minus beta divided by z. Z we find, beta we PC we now know. Okay, so now we can calculate any observable we want. Okay, so now let us take some calculations on some observables. Okay, so what we do now is that calculate some of the observables. So if you know the probability of a configuration in the stationary state configuration, can you calculate the observables? So let us define what are observables. Okay, right? Observables are some property of a configuration, right? Like energy is a property, right? If I give you a configuration, so you can just take a product and make a sum, right? That will give you the energy. Similarly, you can think of doing something else, like how many total plus are there. That is observable. Like in a configuration, how many plus are there? It is observable. Okay, or you can ask that how many consecutive, how often. Let us say if it is Ising model in an Ising system, you can ask a question like how often you find 3 consecutive up spins. 3 consecutive plus in a given temperature, right? So that it can be observable, right? So those are properties of the system. So observables, again, like energy, they are not now independent. They are independent of time, right? For the timing, what I am saying is that given a configurations, you ask a question, and that question has a different answer for different configurations. So if you take this configuration, the value is like if I say plus 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 all plus on a ring, how many consecutive pluses you find? 3 consecutive 3 pluses you find. Now, right, if all the configurations are plus, like how to count it. So basically consecutive 3 plus basically means that you count this one and 3CL, all of them are plus. This is one configuration only. Why? It's a periodic boundary condition. L. Because you just shift this one wherever you like. This wherever if you call it the same length, wherever you put now, you get a 3 plus. So there are L. So if you have different configuration, number is different, right? So question is that what is the average of that? You can ask a question like, what is the average of that? Right? I mean, that is one observable. You can say that how many plus are there? Right? I mean, so here also it is L. In a different thing there are different L. So you can think of these are observables, right? I mean, different observables. So observables are some property of configuration. So observable depends on configuration. There is no time dependence here, right? I mean, doesn't matter what is the temperature. If you are asking how many consecutive plus are there in a given configuration, that's a given number. That doesn't depend on anything. Okay. So the time dependence could have come in probabilities, because probabilities can evolve with time, not the observables. Okay. So basically, but just because you are a stationary state, time is gone here, and if you want to calculate the average, all you have to do is that if you have to calculate some observable which depends on the configuration, and its configurational average you want to calculate. So that will be just P of C, probability that you are in that configuration, and the value of the observable in that configuration. Summation over C. That's what you do, right? Probability that you are in that configurations, and then the observables. Okay.
Why does the left hand side carry index C? I mean, you have some
A sum of the C, right? I mean, just kind of, just to note that average of that, right? I mean, okay. Yeah, O over N. And it's not particular configuration, but when I'm writing it O of C, right? I mean,
No, that's correct. I agree.
no, I'm just saying that X average is 3, but you have to write X. Right? I mean, that's the point, nothing more. Right? I mean, but the number, it doesn't depend on X. X average is 3 doesn't mean that right hand side depend on X. So it's okay, you can write O of C or whatever, it's notational, not pro. So OC PC, okay. So here I just wanted to point out some confusions in these quantum things, okay. The quantum things also you are exactly doing that, okay. So what do you do? So you have in quantum levels, like in energy levels, E1, E2, E3, E4, En, whatever. So now if you want to calculate what is the average value of some observable, how to do? Probability you are in that state times value of the observable in that state, right? I mean, that's what you do. That's what also you are doing here. Probability you are in that state, so which is Pn, which you are writing Pn, that's the probability that you are in the state N, energy state N, and value of your observable in that state, that's the value A, N, N. If you are in state N, the value of your observable in that state is N, A, N, and then you have to summation over N to get the average. So I was not really getting what was the confusion there. Right? I mean, this is a very simple one, and in books particularly make it. I mean, some books make it very complex with words like density matrix and this and that. It becomes very fearsome sometimes. Like you are introduced to many new words at the same time. If you start quantum statistical mechanics, so all you are doing is just that, right? I mean, so there is nothing here. Okay, so all you want to know is that PC O of C, and then let us try to calculate some observables. And okay, so let us try to write one more step. So what is that? P of C is given by here, e to the power minus beta this. So you write that. So that is e to the power minus beta E of C. Okay, and then summation over OC divided by Z, summation over C, right? Is fine, right? I mean, I'm just replacing PC by this divided by Z. Okay, this is the whatever in the down you call it Z. So basically, I write it again. Let's write it more clearly. So this is summation over C, OC e to the power minus beta EC divided by Z, or equal to, also you can write it summation over C e to the power minus beta E of C. It's explicit. Okay. So that's what your observable is. So this divided by Z. Okay. So now let us try to calculate a very simple observable. Okay. So let us say that so observable is, let us say, summation over SI. So S5. Okay. So you have an Ising chain, and that whole system is kept at a temperature T. All you want to measure is that what is the average value of S at fifth site. So you have a variable s, and at fifth site it can be sometimes plus, sometimes minus, right? And given temperature, how often it is plus, minus how often it is minus, because if you're putting s average, that's the meaning of it, right? I mean, how many pluses are there compared to minus, like subtraction of that, that's magnetization. So if you want to calculate S5 average, okay, so that's what you want to calculate. So what is the step is that you just write this observable of OC, doesn't matter how big is the configuration, it's just S5. O of C is now S5, right? Because in a configuration, whatever is written here, whatever written in the fifth site is your value, right? So in this S5, if you want to calculate this equal to what, then your O observable OC equal to just S5, right? I mean, it is just S5. So let us calculate what is the S5 average, okay? So now what you do is that you have to put S5 here and do the sum again, okay? So now we have written the sum, e to the power minus beta is C, it's written here, and it's also written here, whatever. So now let me again complete it, right? I mean, S1, S2, S1, I'll do the sum again. So what I'm calculating is the S5 e to the power minus beta is C summation over C. So I just do erase that, okay? So what I want to write is that S5 e to the power minus beta EC summation over C. That's what we want to calculate. So if you want to calculate that, it's only S5 will be multiplied here. So S3, S4. I have to write a lot. So let us say that instead of S5, can I take S2? Okay, then I don't write more. S2 average. Okay, so my observable is S2. I mean, we'll see. My observable is S2. So now I put S2 here. So this sum contains the earlier sum, contains summation over S1, S2, SL, and this one is S1 T S2, and the next one, all these terms, let me write it, S2, okay, S2 T S3, like that, this kind of sum, S3 T S4, like that, and then finally SL T S1, this is the last term, okay. So it's in a periodic thing. In an open thing we will do it again, but now this is, I have to put a S2 also here. So S2, because I want my observable is S2, so let me write it S2 here. So this S2 will also come here, like, So now what happens is that earlier there is a completeness relation which I was using and taking away all the sums. So I can take this S3 sum using completeness relation, this becomes identity, S4 will become identity, SL become identity, but this one I cannot take, okay. So what is this term? This term is just plus, so if I take a sum here, so let me take S2 sum here, because S2 appears only here, so I can take a sum here S2, okay, and let me see what this matrix is, right? I mean, this matrix is sitting here, T, this matrix T, and then T to the power L or whatever is written, right? I mean, okay. So what is this matrix? So this matrix is that S2 can be plus minus, just replace that, plus, S2 is plus minus. So that is basically plus plus with a plus sign and minus minus with a minus sign, okay. So this one, you know that this is 1 0, this is just 1 0 0 0, and this is 0 0 0 1. So this is just minus. What is this matrix? Sigma G. Okay. So this matrix is sigma G, and then S1 T sigma G. So let us write that. So this is equal to, let us don't take this sum S1 here. So we still have S1, and then you have T, and then you have sigma Z, and then still T is there. And how many T's are there after that? T to the power L minus 1, T to the power L minus 1, and then again S1, okay? And then summation over S1 is still there, okay? So this is again a trace, right? I mean, S1 and S1 you can trace it out. So this is trace of T sigma Z, okay? T sigma Z, T to the power L minus 1, That's what I get. Okay. So now what is S2 average? So basically S2 average is this divided by the partition function, right? I mean, so S2 average equal to trace of T sigma z T to the power L minus 1 divided by trace of T to the power L. Okay, so that's what you get. I'm just saying, instead of 2, if you would have given 3, then in third place you should can you write that, right? I mean, instead of sigma z coming here, it would come somewhere else. Okay, so that will be T to the power 4 sigma z T to the power L minus 4. So similarly S3 S5 Sk any k Sk expectation. So this equal to trace of T to the power k minus 1 sigma z T to the power L minus k minus 1 minus k plus 1, I mean minus of that, total is L divided by trace of T to the power L. But trace, has a cyclic property, right? So this one can be written as sigma z T to the power L, right? I mean, so this equal to sigma trace of sigma z T to the power L, because this can go here, it's just cyclic. Okay, so this one can also go here. Okay, so this is trace of sigma z T to the power L divided by trace of T to the power L, but this one is also same, right? Because this one T to the power k minus 1 goes here, this is also trace of sigma z T to the power L divided by trace of T to the power L. Okay. So now question is that doesn't matter where, I mean, of course this was this you expect physically, because it's just a ring, doesn't matter where you pick up the point, this point is same as any other point in the system, right? So even if you measure at a site 5, you would not know whether it is 5 or 10, right? The name of the site doesn't matter, they're all uniform. So basically that's what you get. So you have S is that, okay? I wait for, this is fine. So now question is that instead of finding S2, okay, let us find it, what's the value? Can we find that? So now what is, let us calculate that, trace of sigma z T to the power L, okay? So can I find the value, okay? So trace of sigma z T to the power L, and sigma z is a matrix like that, plus plus minus minus minus, right? So T to the power L, if I put plus plus, so this equal to plus T to the power L plus minus minus T to the power L minus. You agree with that? I just feed sigma z. Let me one more step, if you want I will do that. So one more step is like the sigma z I put, let us take only this term was there. So if you put it here, this will be matrix plus plus, but trace is again cyclic. So you can say the plus T to the power L plus this term. I mean, all I'm using is the trace of plus T to the power L equal to plus T to the power L plus. You just putting it the other way, okay? So that's exactly that, okay? So this is plus T to the power L plus minus T to the power L minus. That's what it is, okay? From this one you get the same, there is a minus sign, and from this one this is just that, minus minus, okay? So now T to the power L for general L, I mean, and this term plus plus and minus minus, which is the diagonal element. So the diagonal elements, it's a symmetry, so the diagonal elements are the same, okay? So this term is identically 0, okay? So 0, 0, do you like it? So basically it doesn't matter where you measure in the system, irrespective of the temperature, the value is just 0, magnetization is 0, okay? So 0 magnetic state is a T equal to infinity state, like it's a disordered state, completely disordered state. The whole system is disordered at any temperature, right? Except at T equal to 0, because when T equal to 0, then beta becomes infinity, and these calculations has less sense. So you have like everything is up. If T equal to 0, everything is either up, because that's T equal to 0 ground state, it's all either up or 0. So basically if you want to see magnetization, you want to plot magnetization versus temperature, S average is called magnetization. So magnetization versus temperature, it will be 0 everywhere and 1 here, Okay. So there is, right, there are two phases, like, one is at t equal to 0, this magnetic phase, ferromagnetic phase, but then there is no way to transit, what you call phase transition. There is no space here, t equal to 0 is the end point, you cannot go below. So this is the point, and one can describe a little bit of phase transition here, and one can find that then the correlation length of the system actually diverges when you go to t equal to 0 point. Okay.
If you go to 1 plus epsilon dimensions, whichever that is can be defined, then there is a finite TC.
There is a finite TC, yeah.
Of order,
yeah.
goes to 0 as epsilon.
Yeah. Okay. So you got the remark? The remark is that it's only 1D, it is strictly 0. If you put any dimension, little epsilon, like which you can do, then it is non-zero. TC is non-zero. So this point actually, so that transition point, if you call TC, then TC equal to 0 here, right? Because everywhere else it is, so the transition happens exactly at t equal to 0. Okay. So now the point is that if it is not in 1D, 1 plus epsilon dimension, then it will shift somewhere here. It is a finite TC. Then you have two different phases well distinguished, like ferro, and this side is para. So you have a phase transition there because TC is finite. Okay. Oh, why I put sigma z? Because this one is sigma z. Because all I want is that S2 expectation value. I put S2 here. S2 summation over S2. That is just plus plus, because if you put S2 equal to plus, this is plus plus plus, and with a plus sign, minus minus with a minus sign, minus minus with a minus sign. And these vectors are I multiplied once. This vector is just 1 0 0. This vector is 0 0 0 1. So this is 1 minus 1 is sigma z. This is sigma z. Huh? 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 What is SZ? No. Okay. So if you don't let us. Some people identify. Wait a minute. Some people identify this as a matrix which is already known to be Pauli matrix, which is sigma z. You call it P. I don't have a problem, right? One can call it P t to the power L, but the matrix is just that one. There is until now I have never uttered any word about SZ. There is no SZ here. Oh, sorry. Okay, this is 2. Seconds place. Okay, 2 has a problem also. I should have taken 3. Yeah. So S2, expectation value of S2.
So which is on the box is also S2, I suppose.
S2, yes.
It's only S2.
Then how S2 and sigma z's are connected?
That's just a name for this matrix.
No. I think this we can discuss later. Yeah. Okay. I think this one I can calculate it. Right. If you know what is this value, this vector is just this one, right? This plus is 1 0, this plus is 0 1 1 0, and this is minus, and this one is 0 1 0 1 0 1, and this is also 0 1. You multiply, you get whatever matrix you get the matrix as sigma z, which you already know. If you don't want to name it at this stage, it's okay. Call it P, that matrix, whatever that matrix. Okay. So if you call this matrix as A, this is a matrix that you understand, right? This is a matrix. So T A t to the power L minus 1. So T A, let us don't call it sigma z. T A t to the power L minus 1. That's all I'm doing. Okay. Okay. So now I think I can do the. So now there is two. It up to 1 o'clock, right? Okay. So so let me. So magnetization is 0 here. So there is nothing interesting comes up here. Okay. Other thing you can say that what will be the correlation functions, right? You say that.
One simple thing. You can of course generalize this calculation if you also have a magnetic field there, right?
Yes.
Then
Yes.
of course you will have a magnetization.
You have a magnetization.
Calculate by this method.
Yes. can be calculated by this method. So basically, the point is that in this Hamiltonian, this is one term. You can put another term. The point is, if you take another term, summation over h, let us say summation over I SI. This is also, you take energy is the product of these things, this interaction part. It's also sum of all whatever is written, plus, 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 whatever. That sum also, if you take, you can still do the calculations, right? I mean, you have a different t there, right? I mean, you have a different t there, and you can calculate. Only thing which becomes little tedious, because this u will not be that simple. It's not just numbers. It will now depend on temperature and the field. Okay, so that eigenvalues will depend. It's 2 by 2. How complicated it can be, but whatever complicated, that complication comes only if you put h equal to 0. It will not be numbers. This matrix will be different. Eigenvalues will be different, but that doesn't bother us much. Eigen vectors will be complicated. So when you need eigen vectors, it will be little complicated. Okay. So I will give you another problem which I expect you to do. Okay. Right. I mean, in my tutorial, by the way, either you ask me questions or I will ask you. Okay. So it is one of them. So I'll be doing only that. Okay. Yes, all everywhere, doesn't matter, but that is kind of S2 is same. But first thing I proved that S2 has to be same as SK. That problem is independent of, right, I mean, because that is expected. Value we will go later. S2 expectation value has to be same as S3 expectation value, right? I mean, because it's homogeneous and it's a ring, but will it be same? Now the question is that will it be same if you fix the spins at the boundaries? Okay. Let me ask you this question. Repeat the calculation. Find out SK expectation value for the boundary condition that first one is plus, this spin is plus, and this spin is minus, not plus. This is plus, and this one is minus. That is the boundary condition. There is no periodic one. These two spins are fixed. Okay. Given this, so now it is inhomogeneous, right? Because if it is plus here, then this side is trying to always plus. The neighboring one try to align with this one. So that this one try to align with this one means that it will be more like plus. But if you go to the other side, those spins will try to align with the other one. So it will be minus. So at each point, if you want to calculate magnetization, the magnetization will be will be k dependent where you measure. Okay. So can you measure that? Okay. And can you get me the maybe you can plot that. Can you give me a plot of how this function behaves when you at different temperatures? Okay, and that's the homework. Okay. Okay. So I will. So second thing we will like to do is that correlation function. For open boundary condition, I have defined an open boundary condition case. The partition function which also I have written here, S1 SL, and then S1 I fix now. So S1 is plus, SL is minus. That's all I fixed. So now, what is S2 expectation value? It will be just, it will not be trace. It will not be trace anymore, right? Because trace was here. This trace was continuing, right? Now it will be something like plus minus, okay? So do that calculation, right? I mean, calculate the same way what is S2 expectation, what is S3 expectation, in general, what is SK expectation value, okay? That will be a function of k. It is not anymore 0 everywhere, okay? So how do the function look like? That's kind of one question. Second thing I want to calculate is that correlation function, okay? So how to calculate the correlation function is that, so basically instead of saying that S2, right? I mean, you say that S2 and in a different site, given that it is S2 equal to plus, what is, how often you find plus here? Something like that, at a distance k, okay? So that I think will not be, it will not be possible now. But I will just give some other thing, and then correlation function we will do later. Okay. So try to calculate, like all you have to do is that you have S2 which you want. So basically instead of S2 here, let us say S2 and S7. If you have that, how does the correlation function look like, right? So whenever in the second place you have a sigma z, and the seventh place you have a sigma z. So it will be trace of second, because because it is cyclic, trace is cyclic, you can directly come from sigma z itself. So at sigma z, and then at fifth place, then t to the power whatever 7 minus 7, 2 to 7, that is 5. So that is all of them will be t, and then the fifth there is a t to the power 5, right? So that will be sigma z t to the power 5, and then there is a sigma z, and then t to the power l minus 5. This divided by that, and each t to the power k, you know this formula. This is the one which I have written in the board, so you can just insert them, and then you find out the number. Just multiply here and there, you get them. Okay, so that's a correlation function. That if you have S2, S7, but you can directly calculate S that is same as S. I mean, if you S2, S7 must be same as S3, S8, right? Because you know always you are starting at 0, right? Sigma z is 0. So basically the correlation function will depend only on the distance. That is very clear from this calculation. Value we find, but you know it will depend on the this. This is needed, and then now we will also one other thing which you will find that. Can I take few minutes more, like 5 minutes or 3 minutes?
Yes.
Okay. 5 minutes, no 3 minutes. Yes. Okay. So no. Okay.
5 minutes.
No. Sorry. No, it's okay. I'll finish it.
3 minutes after.
So okay. Okay. No. I'm just joking. So now that is that thing can be calculated. Okay. So I still would like to try that calculation, because it will help me. Please help me in my next class. Do that calculation, try that, and we will do it in the next class, because we want to see that how these eigenvalues. You see the partition function has two eigenvalues. Okay. So let me say one thing. So in a periodic system, so you have z equal to lambda plus to the power l plus lambda minus to the power l. Why 2? Because the dimension of the matrix is 2. Okay. So now let us say suddenly in the same model I want to change that this is say 3 variables. Okay. Then there will be the you can write it as a transfer matrix of 3, right? 3 by 3 transfer matrix. You will have 3 eigenvalues. So you have lambda plus, let us say lambda max, some one, whatever the maximum lambda max, and next one is lambda next max, and then plus lambda next max. Like that, I mean, I don't know, some eigenvalues will be there to the power L. That will be the partition function. Simply, you have to find the transfer matrix, find the eigenvalues, and this will be the partition function. But these kind of partition functions, like so this equal to, okay. So this is general, but I'm just saying that again I come back to lambda plus to the power L plus lambda minus to the power L, just for the case I'm studying. So this can be written as lambda plus to the power L times 1 plus lambda minus divided by lambda plus whole to the power L. Okay. And lambda plus lambda minus, you can see that is e to the power beta plus minus e to the power minus beta. Okay. So this is where is I think I erased. So lambda plus minus, this equal to e to the power beta plus minus e to the power minus beta. So lambda minus is always smaller than lambda plus. Okay. So this one is always smaller than 1, lambda minus by lambda. Okay. So if you take L goes to infinity, very large L, so then this will be this is equal to lambda plus to the power L. So even if you have 3 of them or 5 of them, if you take lambda max to the power L, each of them the ratio is less than 1 to the power L, and all of them will go to 0. Okay. So as long as the maximum eigenvalue is well defined, I mean well separated from the other ones, right? I mean the ratio is less than 1, you will have only lambda plus to the power L. Okay. So the partition function takes only largest eigenvalue to the power L. Okay. Yes, good question, will come somewhere in the next class. Okay. So it will not, in this kind of system it will not, we can prove it. Okay. It will never be degenerate under certain conditions. So that what, and so basically as long as this one, okay, let me answer it, then it will not get, if you know it, you get it. So Perron-Frobenius theorem. So, so basically it will not be, so it will be non-degenerate. Okay. So lambda max to the power L. So always the partition function gets the largest eigenvalue of T, the name T, that's what I call transfer matrix. Okay. This is the transfer matrix. Okay. So the partition function only gets largest eigenvalue to the power L. Okay. All I want to say by doing this second, this calculation on correlation function, that the correlation function will get, will have this information of the second largest eigenvalue. Okay, so I want to say that the correlation function, if it is a correlation function, let's say this Si and Si plus R, you write it like that. Then it is distance is always R, separation is R. So this is a function of R that we saw there. So this will be C of R, but C of R will be proportional to lambda plus by lambda minus, lambda minus by lambda plus to the power R. It's the exponential function, and second largest eigenvalue, the next whatever the next makes, that will come there. That's the dominant one. Okay, other terms will come because they are less dominant. So for large R, this is the function always. So this is I wanted to prove. Just do the correlation, for Ising model, and in general, all kind of model. This is one point. Second point, second point is the trace. So Z equal to trace of t to the power L. It's like that, right? So this you can think, or in an open boundary condition, you can say that this is t to the power L, and then some vector here A and some vector B there. It can be plus minus or whatever, S1 and SL. Okay. So this t to the power L, you can write it t like that, right? Okay. So you can see that this is a vector operated by a matrix many times. Does it remind you anything? For example, if you have a two-level system, you have a vector which is a it's a two vector, okay? And then if you have a Hamiltonian for that, the evolution of this will be some unitary matrix which will be operating with time, continuous time. If you think that the discrete time, then it is just some e to the power u, e to the power iu, e to the power iu, like that. This kind of matrix will multiply. So what you get is a partition function. So this t is at each space point you have a matrix t, right? So for the time being, if you drop that idea, you just think that this is one vector and this is time. Then you can think that this is the evolution of this vector with time. I mean, whether you take this or don't take this is a different one, right? So basically, what I'm discussing is a one-dimensional statistical physics, and that will be same thing as a zero-dimensional quantum systems, okay? Because it's a single vector evolving with time. So the interpretation is the same. So there is a general statement as a d-dimensional, d plus one-dimensional statistical mechanics is equivalent in some way to d-dimensional quantum mechanics at the statistical level, okay? So that's the kind of, so if you have a two-dimensional one, of course the transfer matrix will be very large, but the one of the space you can reduce. So if you have a one-dimensional transfer matrix, right, something is evolving in time. So that's one dimension is reduced. We'll come back to it more later. My time is up.
Since you're asking them to think about correlation function and what it is, can they relate the definition of correlation function to a joint probability?
Okay.
Namely, the joint probability that both spins are parallel.
Okay.
What is the exact relation? So the event should be that both spins are parallel. Either both up or both down. That is a certain number. Can they relate it through a simple equation to the correlation?
Okay. Okay.
I mean, can you say it clearly?
Okay. Yeah.
I mean, repeat it clearly because they will not have heard.
No, I think it is. I think I'll do it in the next one so that it will, when you calculate it, it's better. Probably.
You will do it.
Yeah.
Okay. Thank you.
Yeah.
Actually, can I just add another comment? I mean, so suppose I again take this chain, since you also talked of these free boundaries, right? So let's say I fix one of the spins to be up, right? And then I put it at finite temperature. And then I calculate the magnetization profile. That also would give me the correlation length, right? Just by using a single.
Yeah. That is true. Yeah. Okay.
Thank you.